Hello, my name's Thanom and I'm from UNSW. Today I'm working through some of the MATH1011 calculus questions from the section on integration and areas. In question 6 we're asked to evaluate a variety of definite integrals, and I've just chosen parts B, L and O to do in this video. So in part B we're asked to find the definite integral from log base e of 3 to log base e of 4 of the function e to the 2t dt. Remember, finding a definite integral is about finding the area under this curve e to the 2t from the value log of 3 to the value log of 4. So when we calculate this, we're calculating the area here. And remember, the Fundamental Theorem of Calculus tells us that if we want to find that area, we just need to find an antiderivative for e to the 2t, substitute in the limits and find the difference, and that will give us that area. So we need to find an antiderivative of e to the 2t. We know that e to the x integrates to e to the x, or antidifferentiates to e to the x. So we suspect e to the 2t antidifferentiates to e to the 2t, except it doesn't quite. You need two lots of e to the 2t to antidifferentiate to e to the 2t, because we need to apply some sort of reverse chain rule. So if I want to calculate this, I really need 2e to the 2t to be able to find an antiderivative. I need the inside of that function differentiated, sitting there, but I can't change the question. So I'll multiply by 2 and multiply by a half, so I don't change the question there. Now, an antiderivative of 2e to the 2t is indeed e to the 2t. So to calculate the definite integral, we find an antiderivative, and now we'll substitute in the limits and find the difference there. Okay, we can check this antiderivative by differentiating, and we'll see that the chain rule applies and e to the 2t differentiates to 2e to the 2t. So you can always check your antiderivative by differentiating. Continuing with our calculation, we'll have half of e to the 2 times log of 4 minus e to the 2 times log of 3, and e to the 2 log of 4, I can simplify this. This is e to the log of 4 squared minus e to the log of 3 squared. So this is using what I would call the upstairs downstairs logarithm rule. So I want to do that because e to the power of log of 4 squared is just 4 squared, right? Remember, exponentials and logarithms are inverses of each other. So this is really just half of 4 squared minus 3 squared there. So 16 minus 9 is 7. So 7 on 2 is the final value of that definite integral from log 3 to log 4 of e to the 2t dt. So that is in fact this signed area under the graph. Moving on to part L, we have an absolute value function here. So we're integrating from minus 3 to 3 of this absolute value function. So this absolute value function changes rules at minus 2. Okay, so it's x plus 2 as long as x plus 2 is bigger than minus 2, or that is x is greater than minus 2. So the rule on this side is x plus 2. However, if the x plus 2 is negative, that is if x is less than minus 2, then its equation is minus outside of x plus 2 or minus x minus 2. So it changes equations here. There's two ways we can approach it. We can split up this integral and we can calculate it using the Fundamental Theorem of Calculus, which we will do, and then we'll check using a second method, because remember, this is just calculating the area, the signed area under the graph. So these are just triangles here, so we can check our integral by checking the areas of these triangles and seeing that we get the same number. Okay, so let's first of all use the Fundamental Theorem of Calculus. First of all, the integral from minus 3 to 3 is the same as the integral from minus 3 to minus 2. plus the integral from minus 2 to 3. So I'm going to split it over these intervals because that's where the function x plus, the absolute value of x plus 2 changes rules. So from minus 3 to minus 2, it's really the function minus x minus 2. And from minus 2 to 3, it's the function x plus 2. Okay, so I can apply the fundamental theorem of calculus, which just says I need an antiderivative of this. So an antiderivative here is minus x squared on 2 minus 2x. And we have limits from minus 3 to minus 2 here. An antiderivative of x plus 2 is x squared on 2 plus 2x. And I have limits from minus 2 to 3 here. Okay, so substituting in these limits and subtracting, we get minus 2 all squared is 4. So this is minus 4 on 2. Subtract 2 times minus 2 is minus 4. So that ends up as plus 4. Minus, when I substitute in minus 3 there, I'll have minus 9 on 2 plus 6. And over here, I will have a 9 on 2 plus a 6, and I will subtract a 4 on 2 minus a 4. I just want to calculate these sections separately because then it will be easier for me to check my answer. So here I have a 2 minus, and this is minus 4.5 plus 6 is 1.5. So 2 minus 1.5 is a half. Plus, over here I have 4.5 plus 6, so 10.5 minus 2 is 10.5 plus 2, which is 12.5. So my total definite integral is 13. Now, so that was using the fundamental theorem of calculus, and we had to split our integral into two sections. But remember, it was just the area under this graph. Now that makes sense because this triangle on the left here has a base of 1 and a height of 1. So it certainly has an area of half times 1 times 1. Half the base times the height, which is a half. So that matches this half here. And we can see if we wanted the area of this section, that triangle has a base of 5 and a height of 5. So its area is half of 5 times 5, or 25 on 2, or 12.5. And that matches this section here. So we can see that in fact our signed area is 13, and that matches the definite integral that we calculated using the fundamental theorem of calculus there. Moving on to part O, our final part, we're finding the integral of 1 over 9 minus x squared, and we're finding the definite integral actually from minus 3 on root 2 to minus 3 on 2. So this is what the graph of 1 on 9 minus x squared, the square root of 9 minus x squared looks like. We're finding the area bound to the x-axis between those x values there. The signed area, so we would expect it to be positive. So by the fundamental theorem of calculus, we just need an antiderivative. So an antiderivative of 1 on the square root of 9 minus x squared is inverse sine of x over 3. So we can use our standard integral page there. So on our standard integral page, this would be a squared minus x squared. So a would be 3, and the standard integral page says it's inverse sine of x on a. Now we're going from minus 3 on root 2 to minus 3 on 2. Substituting in our limits, we'll have inverse sine of minus 3 on 2 divided by 3 is minus a half. And we're going to subtract inverse sine of minus 1 on root 2 there. Okay, so we just need to calculate this. The angle that sines to give a half, that's pi on 6, but we want the inverse sine of minus a half. So that's going to be in the fourth quadrant there. So that angle is going to be minus pi on 6. And we're going to subtract, again this is going to be in the fourth quadrant because it's inverse sine of a negative, and that angle's pi on 4. So this is minus pi on 4 there. So overall, if we were just going to calculate this, I just might make a common denominator of 12. So this is minus 2 pi plus 3 pi, which overall is pi on 12. So the value of this definite integral, or the signed area under this graph here, is pi over 12. So remember, the fundamental theorem of calculus says we can calculate these areas or these definite integrals by just finding an antiderivative. So we need to be able to anti-differentiate the functions and substitute in the limits and correctly calculate those differences.